Okay, we had a look at group 7, didn't we, a while ago? I'm guessing group 1 is kind of done to death in GCSE. You do a lot of studying in group 1. It's there in the syllabus in periodic table and chemical change and all that jazz. So maybe AQA thought, well, it'd be nice to have a bit of a change. Beryllium. It's a bit odd. I'm not going to go into this in a lot of detail because it's not on the syllabus. It used to be on the syllabus, and if you go back to old exam papers, you'll see lots of questions about beryllium. If you just think about the periodic table and how do we divide our periodic table into metals and non-metals? Where's that line go? Where does it start?
Between aluminium and boron.
That's right. So my division goes like that, doesn't it, down the periodic table in a step. But if you think about that, so that line is right next to beryllium. It's the next atom on the other side, which means that beryllium's actually is a bit weird. It behaves a bit like a non-metal sometimes, which means it's odd. And you don't need to know about the fact that it's odd. I'm just saying it because I'm going to pretty much ignore it whenever we're talking about group 2 elements. Okay, so beryllium's not really going to get a mention. So whenever I'm talking about trends and solubility and different reactions and stuff, I'm going to be focusing on magnesium to barium. Beryllium's odd, it's not on the syllabus, so we're just going to ignore it. Okay, so for the remainder of our focus on group 2, let's just focus on magnesium to barium. We already know quite a lot about the trends of magnesium to barium because we've just done them, haven't we? Somebody tell me a trend going down group 2. Ionization energy decreases. Thank you. Why is that?
Less energy is needed to remove electrons.
Give me the first bit. Just practice trotting those answers out so they just become second nature.
Less energy is needed.
Yes, because as we go down the group, more
shells.
More shells, and therefore more shielding.
Weaker attraction to the
Weaker attraction between
outer electrons.
We're talking about the outer electron, aren't we? When we're ionizing, it's always the outermost or the outer shell electron, please. So weaker attraction between the outer shell electrons and the nucleus. Grand? Another trend? Benji, give me another trend.
The group 2.
Yeah.
Electronegativity decreases.
Super. Now that said, electronegativity is not going to be super relevant for group 2. Why not?
Not very electronegative.
They're not very electronegative. In fact, we might even call them electropositive. But electronegativity is the ability of an atom to attract electrons to itself from covalent bond. How many covalent magnesium compounds do you know? That it's not an element you'd expect to be forming covalent bonds. Actually, it can form covalent bonds, but not during your A level. It can't. And one more trend. Atomic radius. What happens to the atomic radius as we go down?
Increases.
Because
More subshells, which means more shielding. So
more shells. Yeah. More shells rather than subshells. More shells. More shielding.
So there's a weaker force of attraction between the outer electrons and the nucleus.
Super. Okay, that's good. The trend that you would know from group 1, the sort of the GCSE trend, is we talk about reactivity. and that trend holds for group 2 as well, though try not to talk about reactivity. When magnesium reacts, what's happening in terms of its electrons? If I drop magnesium into acid or something and it reacts, what's happening to magnesium in terms of electrons?
It loses 2.
Loses 2. Okay. So if I compared that with barium then, which would do something similar, well, we already know that the ionization energy as we go down decreases. It's much easier to take electrons off barium than it is to take electrons off magnesium. What are these elements behaving as in terms of redox? Reducing agents. They are giving away electrons. Electrons for free. Come along and get your free electrons from barium. So they're losing electrons, so therefore they are being oxidized, therefore they're acting as reducing agents. So what could we say about the reducing strength as we go down?
Increases.
Great. And that's the metals. That we're talking about the metal atoms, not the ions. If we were talking about the ions, something else would happen, but let's not confuse ourselves. So rather than talking about reactivity, which is a bit of a GCSE word, and we know the reactivity series and blah blah blah, let's become a bit more precise and talk about reducing strength. So barium is much more likely to give away electrons than magnesium is. Okay. So that said, let's look at a couple of reactions, and we will actually physically look at these reactions, but probably not today. Okay, not including beryllium. Who can remember how metals in group 1 react? That's a GCSE thing you're supposed to know. Metals and water. Sodium and water. What are sodium and water made?
Salt and hydrogen.
It's not salt. It is hydrogen though. Salt and hydrogen is metals and acid. Metals and water. Sodium and water. We already said hydrogen. It's balancing numbers. Right, so group 2 metals do very similar reactions. So could you have a go at finishing that reaction equation for me, please? Strontium would be pretty reactive, about as reactive as potassium. I'm just going to look that up. Is that right? Strontium is reactive as potassium? (289) 292. They are almost identical in reactivity or reducing strength. Have you done that? Could you tell me the...
So it's SROH plus H2.
What is the formula NaOH? No, that would be, if it was SRO, that would be strontium oxide. It would be the correct formula for strontium oxide, but it's the hydroxide that forms. We're in group 2 now. What does that mean?
Yeah, OH is one, so yeah.
OH2.
S. OH.
What's the ion that we form?
So it's SROH2.
Anything else in that formula that I need to know about?
Is it SROH2?
I'm not sure.
But it's not just SROH2, is it?
Is the OH in brackets?
The OH needs to be in brackets. Because it's 2 OHs for every strontium. Oh, sodium is 1 plus, OH is 1 minus. So NaOH is fine, but we need 2. Yeah. Okay, so reactive metals like calcium and strontium and barium will react with cold water and liberate hydrogen gas, fizz fizz, bubble bubble, squeaky pop. But magnesium, being the sort of the least reactive of the bunch, remember nearer the top, less reactive. Magnesium reacts with cold water very, very slowly. So we can speed that up. By reacting with steam. So that would be water. If we heat it up until the water is steam, so H2O gas, then magnesium will react, and it's quite good fun. But this time we get the oxide instead. So with cold water, I should have said that really, shouldn't I? Cold water, we get the hydroxide. With steam, we get the oxide. This is an odd little bit of the syllabus that's been left behind. There used to be a big topic on the extraction of metals. I mean, it was a whole topic in its own right. That topic went. All that they left was using magnesium to extract titanium. So we use the fact that the magnesium is more reactive, so that titanium ore is first of all converted to titanium chloride, which is liquid at room temperature. That makes CO or CO2, we're not sure. Let's try CO2. Does that work? Yes, it does. Yeah, there we go. Being a liquid is quite useful. It means that that can then be purified by distillation. And then lastly, we use magnesium to reduce the titanium. So that's tickle for it's an odd bit of syllabus that, but it does you do see questions on it around. Just a little thought. Titanium chloride is a liquid. What does that mean? Why would it be a liquid at room temperature? What does that tell us about titanium chloride? Okay, what kinds of substances, when we're thinking about structure and bonding, What kinds of substances have low boiling points?
Simple covalent.
Simple covalent or molecular substances. That's a bit of a surprise that titanium, being a metal, and chlorine, being a non-metal, bond together to make a molecule of titanium chloride. We'll see some interesting chemistry, especially from the transition metals. They can sometimes do a bit of ionic here and a bit of covalent there and mix it up a bit. It's not quite as clear cut as we might have suggested in GCSE. Okay, I think that's a good place to leave that, and then we'll talk about solubilities next time.